Welcome to W211. Previously, we have discussed how to apply the Kirchhoffs current law, Kirchhoffs voltage law, and the Ohm's law together to solve simple electrical circuits. However, there are circuits where the structural complexity hinders the application of these three laws. So, we need a systematic approach to solve some circuits, and for that, there are two interesting methods. The first one that we shall start here is the node voltage method, or known as the nodal method. So let us start with the concept of the node voltage method to solve complex electrical circuits. So consider we have a given circuit. Suppose it is required to find out the current flowing through this 2 ohm resistance. Let us mark the values here as well. This is 5, this is 10, this is 2, this is 10. So the procedure for solving the or for adopting the node voltage method is very simple. First, we need to specify the essential nodes. Remember that the essential nodes are those nodes that are connecting more than three or more than three elements. Such nodes are known as an essential nodes. So we first need to establish and specify the essential nodes. As a second step, we shall mark the reference node. As a third step, we will define the essential node voltage with respect to the reference nodes. With respect to the reference node. So for example, in this particular circuit, we have this is an essential node. Let us call this A and let us call this node B. We have established that this particular point is our reference node, and hence we have marked it with this symbol, with this ground symbol. Next, what we can assume here is that we have to define the essential node voltage with respect to the reference node voltage. So let us say this is the voltage here is VA with respect to this particular point. This is plus, this is minus. Also we have this VB with this sign positive and this sign negative. As a next step, we shall actually, as a fourth step, we shall write down the so here we have two essential nodes A and B, and for each of them we shall write down the Kirchhoffs current law. Remember that we have to adopt a uniform policy for all the essential nodes. For example, we can assume some having some assumptions. We can assume that all the currents leave the essential nodes. However, the current coming from the current source will retain its direction. It will retain its direction. That means that for this particular node A, we have all the currents leaving this particular essential node. However, for node B, the current will leave this node through this 2 ohm resistance as well as this 10 ohm resistance. However, because the third element is actually a current source, so the direction of the current source will enforce the flow of current into the node B. We further assume that following the convention, let us write a convention. Current entering a node is assigned a negative value, whereas the current leaving a node is given a positive sign. With these three things in mind, we shall now apply the Kirchhoffs current law on these nodes A as well as on this node B. This is what the circuit. So we have supposed that we have VA here with respect to this ground terminal, and we have VB here for this voltage. Remember that the key of or the goal of undergoing this whole process is to find out the voltage at all the essential nodes, because once we calculate these VA and VB, it will be a piece of cake to find out the parameters associated with all of the resistances which are connected in this particular circuit. So for equation number for node A, we have this current leaving, this current leaving, and this current is also leaving because there is no current source which is connected with this node A. So we can say this is VA minus 10 divided by 1, and this will correspond to this particular current I1. Let us say this is I5 and this is I2. So for node A, I1 plus I5 plus I2, that is equal to 0. So we have for this node A, we have I1 that is equal to VA minus this voltage of 10 volt divided by this resistance of 1 ohm. Second, we have I5 that is equal to VA over 5, because the second terminal is connected at ground, which is known voltage that is having a 0 volt here. And then for this particular I2, we shall write VA minus VB divided by 2, and that is equal to 0. So this is the equation for node A. Also for node B, we have current I2 leaving this branch, we have current I10 leaving this branch, and we have a current of 2 ampere entering into this node B. So we have for this node B, we have the first thing is VB minus VA divided by 2, because we have earlier assumed that all the currents leave the particular node. So this essential node is also having 3 currents, out of which 2 should leave the node, and because the third element is a current source, so it should feed the current into this particular node. So we have VB minus VA, and that is equal to I2 plus I10 minus 2, that is equal to 0. So I10 is VB over 10, and this is minus 2, and that is equal to 0. So this has given me this equation number 2. Now because we have two equations and there are two unknowns, so solving these equation 1 and 2, we get V1 equal to 9.09 volt and V2 equals to 10.9 volt, right? So now that we have these node voltages available, we can now find out, for instance, we can now find out what is the power dissipated in this 2 ohm resistance. So let us say that the power dissipated in this 2 ohm resistance is equal to V square over R, and this VA, because this is connected between node A and node B, so we shall have the voltage VA minus VB. This will be VA minus VB whole square divided by the resistance R, which is 2 ohm, and that is equal to 9.09 minus 10.9 whole square divided by 2, and this will give you the power which is dissipated in this 2 ohm resistance. So you can see here that this technique is a super simple technique, because it is very systematic and it enables us to get the voltage at these essential nodes, right? Let us say we have a circuit with a dependent source in it, right? So let me draw another circuit. So we have, so for instance, in this circuit we are required to find out the power dissipated in this 5 ohm resistance. But remember that this time we have a current controlled voltage source connected here. Again, we first need to identify what are the total number of essential nodes in this given circuit. As a second step, we shall assign one node a reference node, which is already assigned here. This is an essential node, however, it is assigned a reference node. So we have this node A and this node B, whose voltages are actually unknown. Remember that we don't need to find out the voltage at this particular instant, because this point has a voltage which is equal to the voltage of this voltage source of 20 volt. So we don't need to calculate the voltage here as well as the voltage here, because this is already known. So writing down the KCL equation at node A, we get VA, let us suppose this is VA with respect to this particular point, and this is VB with respect to this particular point. So this is VA minus 20 divided by 2. It will give us the current which is supposedly going away from this node and through this 2 ohm resistance. Secondly, we want to find out what is the current flowing here. So this is plus VA over 20, and then we have a current which is flowing through this 5 ohm resistance. For that we call it VA minus VB divided by 5, and that is equal to 0. So there are three currents, and these three equations identify those currents as a function of VA and VB. So let us call this one equation number 1. As an equation number 2, we have to write down the KCL, or we have to apply the KCL at node B. So for node B, we have all the currents flowing out of this node B. So the first current which is flowing through this 5 ohm resistance is VB minus VA divided by 5. Then we have a current which is flowing through this 10 ohm resistance. We call it VB over 10. And then we have a current which is flowing through this 2 ohm resistance away from this node. So now it is VB minus, this is the 8I phi divided by 2, and that is equal to 0. Now if we see on these particular two equations, this equation has, there are two equations and we have two unknowns, which is VA and VB, and also the value of I phi is unknown. So the method is quite simple. We need to first identify what is I phi. Can we identify this I phi as a function of these essential node voltages? If you see here, I phi is the current flowing from node A towards node B, which means that we can identify this I phi as I phi is equal to VA minus VB divided by this 5. So this will give us the value of this I phi. So if I now substitute the value of I phi into equation number 2, I will get the equation number 2 with only VA and VB included in it. So if I write this as, so if I put this equation number 3 into this equation number 2, I get minus V1 plus 1.6 V2, that is equal to 0. And if I say this is equation number 4, then solving equation number 1 and 4 together, we get V1 equals to 16 volt and V2 equals to 10 volt. Now again, now that we have calculated what is VA and what is VB, it is now very much easy to find out power and the current flowing through any of the elements. So for example, we have the power required is for P of 5 ohm resistance, which is this 5 ohm resistance. So this is equal to, I can calculate it by V square over R, because for that I do not need any calculation of the current which is flowing through this 5 ohm resistance. So with this in mind, if I now want to compute what is P 5 ohm, then P is equal to V square over R, and because on one side we have V1, on the other side we have V2, so the differential voltage or the net voltage across this 5 ohm resistance is equal to 16 minus 10 whole square divided by value of 5, and that is equal to 36 over 5, and this gives me 7.2 watt. I can also calculate this power by first measuring the current flowing here, and for that I need to find out what is the I is equal to V over R, and that V is equal to V1 minus V2 divided by R. So that is equal to 16 minus 10 divided by 5, and this gives me 1.2 ampere. So I can right now multiply this 1.2 ampere with the differential voltage, or I can multiply I square into R to get what is the power which is dissipated in this 5 ohm resistance. So far we have discussed two simple cases here. The first one, where we have applied the concept of the node voltage, and that resulted in two equations. In the second part, we have learned how to actually solve a circuit if we have a dependent source in it. Suppose that we have another circuit here. We have a voltage here, and we have a current source here. If we see that we have three essential nodes here, let me mark this one as a reference node. Let us say this is node A. Let us say this is node A, and this is node B. Now if I write the equation for this node A, then node A is VA minus 100 divided by 0, because there is no resistance connected in this path. So you see here, this path has no resistance here, which makes this particular product, this particular equation equals to infinity. However, the circuit is quite simple to solve, because if a voltage source is connected directly with some essential node, then there is practically no need of finding the voltage for that node A. For instance, this 100 volt is connected directly with this A, and because this particular point is same as that of this 100 volt here, so VA is already known, and that is equal to 100 volt. So this will make the overall circuit more simplified. So we only need to solve one equation for this given circuit, and that is for this node B. So if I write the equation for this node B, then we have VB minus VA divided by 10 plus VB over 50 minus 5 is equal to 0. And with this particular value VA equal to 100 volt, there is only one unknown, that is VB, in this particular equation, and therefore if we use simple mathematical manipulations, I can find out the value of this VB here, and that is equal to 125 volt, right? So if we have a voltage source connected directly with some essential node, then we do not need to write the equation for that node. We should remember that this node has this voltage available, and because this whole bottom line is grounded, so the voltage at this point VA is equal to 100 volt, right? So this is another case of this node voltage method. Let us solve another circuit to see another variation in the circuit. Suppose that we have, for a given circuit, we have more than two essential nodes. Let me draw the circuit. Let us say that this particular node is our reference node, which makes this node, this node, and this node that requires a solution for these three nodes. Let us say this is node A, this is node B, and this is node C. So we need to write down equations for all of these three nodes to solve a given circuit. So if I directly write the equations for this VA here, then we have VA minus VC divided by 2 for this current. Then we have VA minus VC divided by 5 for current flowing through this 5 ohm resistance. Then we have VA minus VB divided by 5, that shows the current for this particular branch. Then this 2 ampere current is feeding the current into this node A, this is minus 2, and we have this 1 ampere current feeding into this node A, minus 1, that is equal to 0. So we have this equation number 1. Similarly, I have to write the equation for node B and node C as well. So writing the equation for node B, we have VB minus VA divided by 5 plus VB minus VC divided by 10 for the current flowing here. Then we have VB over 4 for the current flowing here, and then we have this 2 ampere leaving this node. So I shall write this as plus 2 minus 3 is equal to 0, and this makes me equation number 2. And then for this node C, we have VC over 2 for the current flowing here. Then we have VC minus VA divided by 5 for the current flowing through this branch. Then we have plus VC minus VB divided by 10 for the current flowing through this branch. Then we have VC minus VA divided by 2 for the current flowing here. And also we have a current source of 1 ampere which is going out of this node C through this particular branch. So we have plus 1 is equal to 0, and this makes me equation number 3. If I rearrange these three equations and I separate the variables, then I can represent them in the form of a matrix, and that gives me this particular value. And if I solve these three equations using the Cramer's rules or any matrix, if you go for the conventional method, applying the Cramer's rule or directly going through the calculator version, I will get this VA equals to 7.15 volt, VB equals to 5.05 volt, and VC equals to 3.47 volt. Remember that whatever are the number of equations, if there are more than two equations, we have to adopt the procedure of going through the matrix problem, and by undergoing that matrix problem, we can then thereafter we can solve this given circuit. And after because the main goal is to identify the voltage at the individual nodes. Now, as a last step, let us see that we have a circuit here. and we assume that this is a ground node. So now we have a node, essential node here and an essential node here. Both VA and VB are unknown and we need to identify the voltage here. In a conventional method, what we can assume here, that VA plus 12 volt is equal to VB. This is from this particular knowledge we know that this VB is at a higher potential than this node A because there is a voltage 12 volt between this node A and this node B. We can assume that there is a current flowing here, I, and thereafter we can apply the Kirchhoffs current law for node A and node B. So for node A, we get minus 1.5 plus VA over 6 minus I is equal to 0. This is equation number 1. For node B, I shall write the for this node B, let me write it here. For node B, we have VB over 3.5 plus 3.5, and then this current I is leaving this node B, so this is plus I and that is equal to 0. Let us call this equation number 2. Now if I add these two equations, then I will straight away get rid of this current I, and thereafter what I get is VA over 6 plus VB over 3.5, and that is equal to this will become equal to plus 2, so this is equal to minus 2. So this is the equation that will be used in conjunction with this condition VA plus 12 is equal to VB to find out the unknown voltage VA and VB. However, if a voltage source is, even if it is a dependent source on an independent voltage source, is common between two essential nodes, a super node can be made. So let me redraw that given circuit. Let us say this is 1.5, this is 6, this is 12 volt, this is 3.5, and this is also 3.5 ampere. Now we have this unknown voltage VA, we have this unknown voltage VB. What we shall assume here is, despite that we have identified two essential nodes A and B, and that they have the voltage VA and VB, we shall assume that we have this node is a single node. So first of all, I shall write from this particular side we see that there are the currents flowing into this node. We shall not assume any current in any direction for this super node concept, just like we did a little bit earlier. Also, we have a current moving away from this node VB. So directly writing this as, this is minus 1.5 plus VA over 6, then I will skip this 12 volt source and I will come directly to this VB plus VB over 3.5 plus 3.5, that is equal to 0. And if I solve this particular thing, this is VA over 6 plus VB over 3.5, and that is equal to minus 2. If you see here, this equation A is essentially the same as that of equation, let us call this equation A prime. So you see that if we have a voltage source common between two essential nodes, we can create a super node that further simplifies our given circuit. So we shall stop here, and in the next class we will discuss how we can actually compute the unknown parameter values using the mesh current analysis method. So till there, take care. Allah Hafiz.